This lecture is going to cover the distribution of sample proportions. And if we remember, a proportion is used with categorical variables, right? It's the number of successes over the total number of trials. And what we're going to be interested in is we're going to try to estimate a population proportion using a sample proportion. P hat represents a sample proportion. It's the statistical notation. And statistics are usually English letters. Pi, the population proportion, is a Greek letter, and that's going to denote the population proportion. It's a parameter. Now, just so we're on the same page, let's kind of just recap what a proportion is. A proportion looks at the quantity x over n, where x is the number of successes and n is the total number of trials or observations. If you wanted to think about failures, you could just do simply n minus x, the total number of observations minus the number of failures. So in this quick example, a candy enthusiast was interested in the proportion of Reese's Pieces candy that were orange. They took a sample of 20 and 8 were orange. Now, typically Reese's Pieces, for those of you that don't know, there's orange, brown, and yellow. So our successes were 8, our total number of observations or trials were 20, and our failures would be 20 minus 8, or 12. Now, what we're going to be interested in is something that's called the distribution of sample proportions. Let's see what I mean by that. This webpage is going to help represent the distribution of sample proportions. And how we're going to do so is by looking at an infinite candy dispenser. That would be amazing. Where we have Reese's Pieces candy. And suppose 50% of candy in this infinite Reese's Pieces machine is orange. So what we're going to do is this. A pack of Reese's Pieces, a small pack, roughly has 20 candies. So we're going to draw a sample of that, and we're going to find the proportion that were orange. So we're going to draw a sample, and this is going to simulate a random sample. And in this sample, 80% of our candies were orange, or a probability or a proportion of 0.8. The population proportion is 0.5, but our sample proportion is 0.8. Just because your population proportion is some value doesn't mean your sample proportion is going to be that exact value. There's variability to sampling. If we draw another sample, we could end up with a different result. In this result, we got exactly our sample proportion. We can repeat this process over and over and over again. This sample proportion is 0.65. I'm going to simulate this process 10 times. We randomly select 20 orange candies and we plot this sample proportion. Now, in order to kind of make this go faster when I do a bunch of simulations, I am going to hide this candy machine and I'm not going to animate this stuff. And I'm going to do this on a mass scale. So imagine 1,000 samples. We took 1,000 packs of Reese's Pieces and found the proportion that were orange. And so I'm just simulating this concept over and over again, this process over and over again. What we'll notice is we started with a categorical variable. They were orange or were they not orange? But a sample proportion is a numeric variable. It has a value. And so what we'll notice is the distribution of these sample proportions seems to follow a normal distribution. It's following this bell-shaped curve. Our central limit theorem not only applies to sample means, it also applies to sample proportions. But something we need to keep in mind is this as well. Look at where this center is. The center is 0.5. Our population proportion is also 0.5. Your population proportion and the mean of this sampling distribution will always equal the same thing. Imagine, for argument's sake, it was Halloween time and Reese's Pieces said, you know what, we want to have more orange candies than we typically do. So we're going to change the proportion of orange candies. We're going to change it to 90%. So originally it was 50%. Now there's a whole bunch more orange candies. Let's repeat this process where we can sample orange candies, and I'll undo this hide candy machine now. And we can kind of animate this. Now it's way more likely to get an orange candy. There's a lot more of them, right? And we're doing the same thing. We're taking a pack of orange candies and we're plotting it. Taking a pack of orange candies and we're plotting it. The same exact process. Now there's just more orange candies. So I'll simulate this process over and over again. Right? I'll hide the animation machine so it goes a little bit quicker. But we'll notice something interesting here. The number of orange candies is still 20, yet our distribution does not seem to be normal or bell-shaped now. It seems to be skewed to the left. We didn't change our sample size. The only thing we did change was the probability of an orange candy. What happens is the closer your proportion is to 1 or to 0 is going to require you to sample more observations. And this is because you can't have a proportion larger than 1. So you create a boundary at 1. If we switch this to 10%, we would have the same exact process. Now our boundary is at 0. We can't have a proportion less than 0. So it's going to form this skewed distribution. Our mean is going to be at 0.10 of this distribution, but we're going to have a skewed distribution. The closer your probability is to 0.5, the more room you have to your right and to your left, the better it will follow a normal distribution. Something we need to keep in mind, though, is that the more observations we have, the smaller our spread becomes. So imagine now instead we sampled 200 orange candies. And the proportion of orange candies in this example is 0.10. So we'll see a huge simulation, so many orange candies. And our goal is to try to estimate the proportion of orange candies. Now, the more observations we have, the smaller our spread will become. Now, what we'll notice is if we repeat this process over and over again, our distribution seems to now follow a normal distribution. Not only does your distribution depend on your sample size, it also depends on your population proportion. So in order for our central limit theorem to hold, we need to have enough observations sampled given a certain sample proportion. This graph right here is called the distribution of sample proportions because every single observation in this graph was a sample proportion. On top of that, the center of our distribution is the exact value of our population proportion. The mean of the distribution of your sample proportions, of your p-hats, is the exact value as your population proportion. Those two values are exactly the same. So there's some things we need to think about here in order for our central limit theorem to hold. We need to figure out what sample size we need given a certain proportion in order for our distribution to become normal. So it turns out that one of our conditions that needs to be met is that the sample size times p-hat needs to be greater than or equal to 10. So if that quantity is greater than or equal to 10, what that's saying is you sampled enough people given your proportion in order for it to follow a normal distribution. What you also need to consider, though, is your sample size times 1 minus your sample proportion. Think of this as your failure percentage. The success percentage is p-hat. The failure percentage is 1 minus p-hat. And if that quantity is not greater than or equal to 10, you would end up with a non-normal distribution. The last thing that needs to be met is that your sample size actually needs to be at less than 10% of the population. If your sample size was more than 10% of the population, you would actually have to use a different distribution to estimate probabilities and percentages. All three of these conditions need to be met in order for our central limit theorem to hold. In order for the distribution of sample proportions to become normal. Now, we saw in that simulation that if we have some distribution that we're interested in, and we're interested in the population proportion of this distribution, we'll call this a success, the population proportion of successes, and this a failure. Right? What happens is we're actually not using this distribution to study it. What we're doing is we're taking a sample proportion, we take a bunch of observations from this distribution, and from those observations, all those observations, we calculate a sample proportion. And so over here, I'll plot that sample proportion. And we can repeat that process over and over and over again. Taking a sample, plotting the sample proportion of successes. Taking a sample, plotting the sample proportion of successes. And we can keep doing that over and over again. And if we did that enough, we had a large enough sample size given our proportion, this distribution would become normal. The important part of this, though, right now, is that the mean of this distribution, which we'll call mu p hat, the population mean of our sample proportions. Every single dot is a sample proportion. This population mean turns out to be the same value as your population proportion. So what happens is if we can estimate the mean of our distribution, of our sample proportions, we'll actually learn about our population proportion. We know how to figure out probabilities and percentages associated with a normal distribution. And we can know that this is normal if our conditions hold. What we need to consider, though, is in order to calculate probabilities and percentages associated with a normal distribution, we need to figure out the mean and the standard deviation. It turns out that the standard deviation of this distribution, the distribution of sample proportions, is actually a function of the proportion itself. And because we're dealing with a standard deviation of a sampling distribution, we'll call this the standard error. If we wanted to calculate the average distance an observation is from the mean in this graph, it turns out to actually be a shorthanded way. It turns out to be sigma p hat is the standard deviation of sample proportions, and sigma represents a population. So it's the population standard deviation of sample proportions. And it turns out to equal this function right here, pi times 1 minus pi over your sample size. The more observations you have, the smaller that spread will become. But typically, we don't know pi. That's our population proportion. We're trying to estimate that. How could we ever know that? What we'll do is we'll use a sample proportion, our sample proportions, to try to estimate our population proportions, and we'll use this sample standard deviation to estimate our population standard deviation. If we can estimate the standard deviation of the sampling distribution, or our standard error, we'll be able to figure out probabilities and percentages associated with our distribution.